So shall we start?
Yes, sir.
Okay. So, am I audible? Can you hear me?
Yes, sir. Yes, sir.
Uh, okay, so where were we? What are we doing? So, we have discussed this, right? I mean, okay, so we have discussed these things. So, game of chance or gambling we were doing. Right? And so here what we are doing that x1, x2, xb sequence of integrable random variable. Xn are your winning or losses per unit stake in game n. Okay. Now, if your stake in each game is one, then Xn are your winning or losses per unit stake. Okay. And if your stake and each game is one, then your total winning of the after in game is equal to x1 plus x2 plus x. Okay. And so S0 is equal to S0, F0, correct? And So S0 is equal to this one. S0 is equal to this F0. And if you played the game n minus one times, so you accumulated the knowledge using Fn minus one. That is the filtration. And the game is fair if this is Sn given Fn minus one is Sn minus one, right? Then it is favorable. Submarginal, right? If the expectation of Sn given Fn minus 1 is greater than equal to Sn minus 1, then it is submarginal, and unfavorable if it is a supermarginal. Okay? If it is a supermarginal. Okay. So this was the thing we were discussing. And, now, so now what it is saying that suppose so it is just now what it says that let hmm, let can vary your stake to alpha in game n. So you can vary your stake in game n. So in the sense that it says that I mean instead of here, for example, here Sn equal to x1 plus x2 plus xn, right? So so in a sense that you are now you will I would say now you will have a weighted thing. I mean, in a sense that you will have weighted thing. So instead of x1, x2, so alpha 1 portion of x1, alpha 2 portion of x2, and alpha n portion of xn. Okay. Uh, so and this alpha is so alpha is can be greater than equal to zero. Okay. Or even it can be negative. So I don't think so. So in a sense that if you do, when you don't play the game, so when you don't play the game, then that is alpha. This thing alpha I can be zero. Okay, and so in a sense that sorry, alpha I can be zero if you if you don't play uh, ith. Yeah. Yeah. So if you don't play, so that means you are not, so that then alpha is equal to zero. And also it can be negative. Uh, Suppose you yourself is the casino. I mean, I mean, suppose you yourself is the. Uh, I mean, you won the casino. Okay? In case you won the casino, and you are accepting the others people's bet. Okay. So it says that so alpha I can be negative in a sense that if you own the casino, so in a sense that uh, you accept you accept other people. That you are accepting the other people's. Okay. So, so, so in a sense that when the I mean when you are uh, playing, I mean so when you have a alpha n this thing, when I mean when you are deciding on the stake of alpha n, uh, uh, I mean you know the outcomes of n minus 1. Yes. So in a sense that uh, so in a sense that uh, so in a sense that so alpha n is f n minus 1 measurable. So it is alpha n minus 1. So in a sense that if n minus 1 uh, so so this represents your knowledge accumulated in n minus 1. Correct. And so this is one so this is one thing. And so if n minus 1 is nothing but your knowledge accumulated till n minus 1 game, right? And this is quite normal to take this f0. This is the trivial sigma algebra. Okay, so it's the trivial sigma algebra. I mean, this is without loss of generality. That so this is f0 is the trivial sigma. So, yeah. So, so therefore, I mean, we can we can have a definition of what is called a gambling strategy. Okay, so it's called the gambling strategy. What is the definition of the gambling strategy? Is a gambling strategy is this alpha one, alpha two, dot with respect to filtration. F1, F2. Is a sequence of random variables that alpha n is measurable, right? And this F0 is equal to empty circle. I mean, this is the trivial. So, so, so you see, the gambling strategy is nothing but it's a sequence of random variable which is measurable with respect to certain filtration, and alpha n is fn minus one measurable. Okay, so this is so so gambling strategy. So therefore, you can when you model any gambling or these things into these things. So this is also, I mean, this tells how probability model or the martingale theory is used for doing this gambling strategy. Okay. So, so in a sense that so, So now, so this is the definition. Okay. Now, uh, now suppose you follow a strategy. Okay. Suppose then 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 suppose you follow a strategy in your total uh, of the games is so it is like I will write it as Sn bar. Okay. So earlier I have wrote Sn equal to x1 plus x2 plus xn. Now I'm writing Sn bar. Okay. Is equal to, so alpha 1 uh, x1 plus alpha 2 x2. Okay. So in a sense that this one is equal to alpha 1, this alpha 1 x1, alpha 2 x2, alpha n x. So, I mean, for I mean, the convention wise, you can have S0 bar is equal to 0. That's convention. Now, one thing so for example here, what is my Sn? S0 here also I have taken S0 is equal to 0, right? And Sn, so S1 equal to x1, right? S0 is 0. S2 is equal to x1 plus x2, right? X1 plus x2. S3 is equal to x1 plus x2 plus x3. So, so in a sense that you can write this alpha 1 into S1 minus S0 plus alpha 2 S2 minus S1 plus dot 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 plus alpha n Sn minus Sn minus 1, right? Xn is not, I mean, So S0 is equal to 0, S1 equal to uh, x1, S2 equal to x1 plus x2, right? S3 is equal to x1 plus x2 plus x3, right? So yeah, yeah. I mean, you see, sorry, you see. So x1 you can always write it s1 minus s0 because s0 is zero, and x2 you can always write it s2 minus s1, right? And similarly, x3 you can write it s3 minus s2, right? I mean, this way you can write. So this is what I have just wrote. That is what I just wrote. So now we'll do one theorem or something like that. So let's do one theorem. Mhm. So what it says that let this be a gambling strategy. Let this be a gambling strategy. Now, there are three parts. First part is if alpha 1, alpha 2 is a bounded sequence. Okay, is a bounded sequence. That means, I mean, alpha I is bounded by some m for all I. Right? Bounded sequence means mod alpha is less than equal to some constant for all I. And 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 is 0, S1, S2, right? Is a margin. Then then S0 bar, S1 bar, S2 bar is also a margin. So in a sense that what does it says that it says that if you if you have a fair game So you see here, sorry. So, so is it visible? Is it visible?
Yes, sir.
So you see, when we define the things, we have defined it like this, right? The game is fair. If it's a martingale, the game is favorable. If it is sub-martingale, it is unfavorable. It is this thing. So that is what says that suppose it is given a fair game. So that means S1, S2, this is a martingale. And then S0 bar, S1 bar, S2 bar is also a martingale. So in a sense that if you have a fair game, you are gambling, it will be a fair game. So you cannot change, I mean, uh, I mean, whatever gambling strategy you use, if it is a fair game, it will turn into a fair game. And you cannot, I mean, this, it is like a, I mean, the game will be fair. I mean, you cannot just change the outcome of this thing. I mean, it's a, uh, I mean, winning loss is, you must realize the fact that, I mean, we are talking about fairness of the game. I mean, we are not talking about the winning losses or who will win, who or lost. No, we are talking about the fairness. I mean, suppose you are tossing a coin. If if the head comes with probability half, but I mean head, I mean the if head and tail comes with equal probability, so that means head comes with probability half and tail comes with probability half. Then we say the coin is a fair coin, right? It is not that I am saying that it always a head will come or tail will, or even if I am not saying that every time you toss you will get head or head first, tail first, or whatever. I'm not talking about that sequence, that strategy. I'm talking about the fairness. So fairness means you toss a coin, with, I mean, anything can become the head or tail, the outcome head and tail are equally likely. That is what it says. It does not say about anything. Okay? It does not say about anything. It says that whatever be the situation, it may head may appear, tail may appear. I mean, appearing of head and tail is equally likely. That is what the fairness means. Okay. And then similarly, so this is number one. Number two, if alpha 1, alpha 2, this is uh, non-negative bounded set, and S0, S1, S2, dot, 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 dot is a super martingale, then S0 bar, S1 bar, S2 bar This is super. This is super. So in a sense that an unfavorable game. So for super martingale, uh, it is unfavorable. The last one, super martingale means unfavorable, right? So and unfavorable game turns into an unfavorable turns into an unfavorable. Okay. Similarly, number three, if alpha one, alpha two is sorry, is a non-negative bounded sequence, and this is a submartingale. Then so in a sense that so submartingale is from the definition, submartingale means favorable. Okay? If you have a submartingale, that means the favorable one. So here a favorable game turns into a favorable one. Favorable game turns into favorable. Okay? So in a sense that this provision says that you cannot really beat the system. A fair game always turns into a fair one. A favorable game turns into a favorable one with any strategy, whatever strategy so you take. So these are, I mean, that means that gambling strategy independent. I mean, and if it's a unfavorable game, it turns into an unfavorable. And this bounded sequence means I mean, sometimes non-negative or this normal bounded sequence, no, but that in the gambling strategy, you start with some money, right? I mean, that money is, I mean, it has a finiteness. It is not that you have, I mean, your credit limit is finite. I mean, it's not that you just have, having, I mean, suppose you go to the this thing with $1,000, 1,000 euro or something. So it means that you have a this thing. This is what it says. I mean that your credit limit is fine. So boundedness implies that your uh, so this boundedness of alpha n implies the uh, your credit limit is finite. I mean, you can have huge money, but it's a finite. You know what is the thing. Like somebody may playing with $1,000, somebody may playing with $1 million, but whatever it is, it's a finite thing. Okay. 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 Let's take a break. Then we'll start again. Okay. ठीक है? Okay.
Yes, sir. Yes, sir.
Am I audible? Can you hear me? Hello? Can you hear
Yes, sir.
me? Okay. So we are talking about this thing. So we are talking about this thing. So if so, a fair game is always a fair one. Unfavorable game is always an unfavorable one, and favorable game always a favorable one. Okay. So so yeah. See, so the way strategy, the gambling strategy is defined. So these alphines are uh, Fn minus one measurable, right? And so yeah, so let's talk about the proof. Okay. So so alpha n is if n minus one measurable, and and so Sn minus one bar, right? So Sn minus one bar. So how these things are defined? This is defined like this way, right? Sn so Sn bar is Fn measurable, right? Sn bar is Fn measurable. That is what it says, right? Sn bar is Fn measurable. So in a sense that Sn minus bar is Fn minus one measurable. Okay. Okay. Now, now what we have to show that fair game is a fair one. So we have to show that this Sn bar is martingale, right? We have to show that Sn bar is so this Sn bar given if n minus one, right, is equal to is so Sn minus one bar, right, plus alpha n xn, right, given fn minus one. Sn bar is equal to this. That's what I mean. That's what we have done. Sn bar is equal to alpha n x. I mean alpha one. Uh, so Sn minus one bar plus alpha n xn, and xn can be written as alpha n into Sn minus Sn minus one. So we'll just write that. Okay. So 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 now we can do the linearity of the conditional expectation, right? So this is Sn minus one bar given if n minus one plus expectation alpha n Sn minus Sn minus one given if n minus one, right? Correct. Right. Now Sn bar Sn minus one bar is Fn minus one measurable and alpha n is Fn minus one measurable. So we'll do those properties. Hmm. So here we need this third property. You see, expectation, conditional expectation of xy given g is equal to x into conditional expectation y given g if x is g measurable. Okay. So if x is g measurable, you can take that out. You can take that out. That is one thing we will make. And another is this. If x is g measurable, then conditional expectation of x given g is equal to x. Okay. So this first property. In this page, first property, and here is the third property. That is what we will do. Okay. So, so that is what we will do now. Okay. So this is if Sn bar is this measurable, so this will be S minus 1 bar, correct? Plus alpha n expectation Sn minus Sn minus 1 if n minus 1. Okay. One minute. Now, so now we will make the things again the same thing. Linearity we will use. Okay. So expectation Sn given if n minus 1, right? Minus. So expectation of Sn minus 1 given Fn minus 1. Okay. So Sn minus 1 is Fn minus 1 measurable. So this will be Sn minus 1. Okay. And this Sn is martingale, that is given, right? S0, so that is what given. S0, S1 is a martingale. So therefore, this part is martingale, correct? This part is martingale. So this will be Sn minus 1. So Sn minus 1, and this will be 0. So this, therefore, this is going to be Sn minus 1 bar. So therefore, this is a martingale, right? Expectation of Sn bar given Fn minus 1, conditional this is equal to this, so therefore a margin. Okay, so hey, this is the first part, proof of the this first part, right? Uh, this is the first. Now, now the second proof. Second proof is what? I mean, what it says that supermartingale, right? So supermartingale means what? Supermartingale means is this one, last one, right? So so this is last one. So so that means so supermartingale implies expectation of Sn given f n minus 1 less than equal to Sn minus 1. Right? That is the supermartingale definition. Supermartingale is this one. So it is less than equal to Sn minus 1. Okay. So then so the from the beginning the calculation will be it will come up to this part. Okay. Uh, so from the cap so I mean here we just so assume let's assume alpha n greater than equal to 0. This assumption you take. Probably we take this assumption at the beginning. Okay, that alpha n greater than equal to 0 for each n in n. We take this. Okay. Okay. Now the calculation from the beginning will be the same. So you will come. Sorry. Ah, sorry. This you will come up to this last step. I mean, before the last step. So you'll come up to this S n minus 1 bar, right? Because we still here we are using the measurability, all these things, not anything. Okay. So we'll come this plus alpha n, right? Expectation is n given if n minus 1 minus Sn minus 1. Yeah, up to this part we will come. Now for supermartingale, this part is less than equal to Sn minus 1, right? This part is so shit. So for supermartingale, this part is less than equal to Sn minus 1, right? And alpha n is greater than 0. Alpha n is greater than 0. So in a sense that therefore this will imply expectation of Sn bar given Fn minus 1, right? Minus Sn minus 1 bar, this one you take this side, is less than equal to 0. Less than equal to 0, right? Because this is less than minus 1 minus, so therefore this part is an alpha n greater than 0, so therefore this thing is negative, so you take this left side and then this. So this will imply that expectation is n bar if n minus 1 less than equal to Sn minus 1 bar. So this implies the supermarket. Correct. This is the supermarket. Similarly, we can prove the submartingale part. Submartingale part we will do. So submartingale. Yeah. So submartingale means the second one, expectation of ah, expectation of Sn given Fn minus 1 is greater than Sn minus. Okay? So there's the submargin. So this is my this thing, and we are given this essence of submartingale, right? Essence is a submartingale. So this is greater than equal to this. Okay? That is the submartingale definition. So this is the definition of submartingale. The submartingale. Now we'll do the again the same calculation. It will so, so same calculation will come up to this loss before this step. So in a sense that this one will come, right. So you have expectation Sn bar given if n minus 1 will be equal to Sn minus 1 bar plus alpha n, right? Expectation is n given Fn minus 1, right? Minus Sn minus. Now, now, because of the submartingale, this part greater than equal to Sn minus 1. N minus 1, right? So this part is greater than Sn minus 1, and this is so therefore this things is greater than 0, right? Because Sn minus this is greater than Sn minus 1, so this part is greater than 0. So this implies that expectation of Sn bar if n minus 1 minus Sn bar and n minus 1 bar is greater than equal to 0. So this implies expectation Sn bar if n minus 1 greater than equal to Sn minus 1 bar. Right? And this therefore this implies submark. And this completes the so this completes the So this is the this thing. Um, so therefore, this is an important theorem about this. About the gambling strategy. So in a sense that you can never beat the system. If it's a fair game, it's a fair game. If it's an unfavorable game, the this thing will be unfavorable. And if it's a favorable games, it's a favorable game. It turns into a favorable. Okay. And so this is gambling. This give you a glimpse of how these gambling things are done in actually. I mean, how mathematically modeled these things. Okay. Uh, so now we will do another important thing, which is called the so, stopping times. Okay, so I think it's better we start it. So let's start stopping time. So what is a stopping time? So stopping time is suppose something you want to. I mean, you are playing some game and you want to quit the game and certain. I mean, after one time, after second time, after third time, like this. Okay. So in a sense, so it's a random variable. Stopping time is also a random variable, and uh, so it's a discrete random variable, and it takes values. I mean, discrete random variable with range set one, two. So so in a sense, you can define it. So so if the so if your random is tau, so I mean, infinity you take because suppose it does not, you never quit the game. You never quit the game. Okay. So it's a discrete random variable. So this tau is a this thing. Uh, so tau is a random variable with values in this is called stopping time. Stopping time. This is stopping time. Okay, with respect to filtration Fn if for each n, okay, one, two, is tau equal to n is Fn measurable. So like this is it's called. So so in a sense that tau equal to n. So it's a, so suppose you decide that you will quit the game after n times. Right? You will quit the game after 10 times. But when you see the result, so suppose you want to, so you are playing a game. Every game you earn something. Like every your game of poker, if you win, you get 100 rupees. You lose, you get you lose, you give 50 rupees. Okay. Now in this game you are playing, suppose you want to get in a position where you have 1,000 rupees. Okay. So whenever you reach 1,000 rupees, you quit the game. And to get that 1,000 rupees, how many times whatever you play this game, that's your stopping time. Okay? So I mean, so in a sense that every thing, I mean, you quit the game after you getting your desirable results. Okay. 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 So this is the idea of stopping time, and yeah, we'll discuss about this more in the next classes. Okay. Yeah, we'll see how much we can do the this. Okay, ठीक है. Let's stop it here today. Is it okay?
Yes, sir.
Okay.
Yes, sir.
Okay. Bye. See you on Thursday. Okay. Thursday we'll meet again.